This video covers whole number theory concepts in simple language and with lots of examples which are required for Math Olympiad as well as other competitive examinations. Hello friends, I welcome you all to my channel. Today I feel pleasure to share a very important as well as interesting topic, modular arithmetic from number theory to you, which is a very basic concept for preparing Maths Olympiad or other competitive examinations. So modular arithmetic is nothing but arithmetic of remainders. Modular arithmetic is a very familiar use in 12-hour clock, in which the day is divided into two 12-hour periods. If the time is 8 hours now, then after 8 hours it will be 16. But do we say it is 16? Simple addition would result 8 plus 8 16, but 16 hours reads as 4 on the clock face because clocks wrap around every 12 hours and the hour number starts over at 0 when it reaches 12. So 16 hours is equivalent to 4 hours when we talk about 12 hours clock. We say 16 is congruent to 4 modulo 12, written as 16, and this is the symbol of congruency, that is same as equivalency, 4 mod 12. We read as 16 is congruent to 4 modulo 12. So in the same way, we can say 16 is congruent to 4 modulo 12. 21 is congruent to 9 modulo 12. 12 is congruent to 0 modulo 12. So what is this congruence? Let us learn more. So today's our video is about modular congruences. Congruence is nothing but more than a statement about divisibility, first introduced by the physicist Carl Friedrich Gauss. It talks about let n be a positive integer. Two integers a and b are congruent modulo n if they each have the same remainder on division by n. We write a is congruent to b modulo n. This is the mathematical symbol. Such a statement is called a congruence. Let's analyze it again. If a and b are integers, may be positive, may be negative, but n is a positive integer, then a is congruent to b modulo n if and only if n divides a minus b. So this is the symbol. A is congruent to b mod n if and only if n divides a minus b, or the difference of a and b is k times of n, multiple of n, or a is equal to b plus k times of n. Some examples. 15 is congruent to 3 modulo 4. That means when 15 is divided by 4, we get the remainder 3. Similarly, 31, if we divide by 4, we get again the remainder 3. 4 7s are 28, remainder is 3. So 15 and 13 are congruent to 3 modulo 4. 15 and 13 are congruent to modulo 4. Let us take another example. 19 is congruent to 5 modulo 7. 12 is congruent to 5 modulo 7. That means 19 and 12, when they are divided by 7, each gives the remainder 5. So 19 and 12 are congruent modulo 7. Another example, 9 is congruent to 2 modulo 7. 2 is congruent to negative 5 modulo 7. That means if I'll divide 2 with 7, then I'll get 2, 7, 1 times 7. So remainder will be negative 5. So 9 and 2 are congruent to negative 5 modulo 7. Let's solve some questions for better understanding. Which of the following congruences are true? First question is 11 is congruent to 26 modulo 5. Whether it's true or false. This is very simple, as we got the definition that n should divide a minus b. Here for this first question, a is 11, b is 26, and n is your 5. We have to see whether a minus b is divisible by n or not. So 11 minus 25, 26 is equal to negative 15. Is it divisible by 5? Yes. So this is true. Next question. 9 is congruent to negative 9 modulo 5. So 9 minus 9, this will be 18. Is it divisible by 5? No. So this is false. Next, 28 is congruent to 0 modulo 7. Yes, 28 minus 0 is divisible by 7, so it is true. Next question. Negative 4 is congruent to negative 18 modulo 7. So negative 4 minus 18. So this will be plus 18, that will be 14. Is it divisible by 7? Yes, so it is true. Next is negative 8 is congruent to 5 modulo 13. So minus 8 minus 5 is minus 13. Yes, this is divisible by 13, so this is true. Next is F. 38 is congruent to 0 modulo 13. So 38 minus 0 is 38. So 38 is not divisible by 13. So this is false. I hope you have understood. Now you can solve some more questions yourself. Which of the following congruences are true or false? 63 is congruent to 14 modulo 7. So you can check 63 minus 14, 9, 4. Yes, it is true. Next is minus 39 is congruent to, so you'll test minus 39, again minus 39 is equal to negative 78. It is not divisible by 7, so this is false. Next, coming to C, 63 is congruent to 14 modulo 12, so it will be 63 minus 14. It is again false. Next is your negative 8 is 16, so it is true. Next is, this is also true. So this is also true. So thank you for watching, and in the next session we'll go for some more. Thank you for watching. Don't forget to subscribe to watch more such videos. This was only the introduction of the number 3. We'll proceed and we'll learn more and more. Thank you. Please keep on watching because next video will be least residue system modular M. Here we'll learn how to find least residue of modular N by using congruences. And why this is useful? This is useful to find the residue of big numbers with big powers when divided by some numbers. So let us begin. Let us recall about modular congruences. Let us recall about modular congruences. It says if a and b are integers and n is a positive integer, then a is congruent to b modulo n if and only if n divides a minus b. So this is the symbol a congruent b modulo n if and only if n divides a minus b. Now let us see what are the properties we can use for congruences to find the residue. First is if a, b, c, d denote integers, m is positive integer, then if a is congruent to b modulo m, then b is also congruent to a modulo m. Second property is if a is congruent to b modulo m and b is congruent to c modulo m, then a is congruent to c modulo m. If a is congruent to b modulo m and c is any integer, then a plus c is congruent to b plus c modulo m. In the same way, if a is congruent to b modulo m, then for any integer, we can write a minus c is congruent to b minus c modulo m. If a is congruent to b modulo m, then a product of AC is congruent to product of BC modulo M. If A is congruent to B modulo M, then AC is congruent to BC modulo MC if C is greater than 0. If A is congruent to B modulo M and C is congruent to D modulo M, then A plus C is congruent to B plus D modulo M. If A is congruent to B modulo M and C is congruent to D modulo M, then A minus C is congruent to B minus D modulo M. If A is congruent to B modulo M, C is congruent to D modulo M, then product of AC is congruent to B times of D modulo M. If A is congruent to B modulo M, C is congruent to D modulo M, then product of AC is congruent to B times of D modulo M. This is the most useful property of congruences, power rule for congruences. If A is congruent to B modulo N and M is a positive integer, then A raised to the power M is congruent to B raised to the power M modulo N. So we'll learn how we will use these properties in solving problems. And some other properties are Fermat-Little theorem, Euler's theorem, and Chinese remainder theorem. In this session, we are not going or covering these theorems. Only on the basic properties we will solve some problems. So applications of these properties to find the least residue of a modular n. The least residue of a modular n is the remainder r that we obtain when we divide a by n. The integer r is one of the numbers 0, 1 up to n minus 1, and it satisfies a is congruent to r modulo n. So here you should keep in mind that when we divide a with n is always positive. This remainder should be also positive. It is starting from 0 to n minus 1. That means the remainder should be from 0 to n. Then n. Now the procedure how to find the least residue. So I have taken 3 questions, and through the example we can understand how to find or what is the least residue. First is find the least residue of 32 modulo 7. So we know that when 32 is divided by 7, it is your 7, 4 times 4 is the quotient and 5 is the remainder. So I'll write 32 is congruent to 5 modulo 7. Or the answer is, what is the least residue? 5 is the residue. Least residue. First one. Now coming to second one. Find the least residue of negative 33 modulo 7. So when it is a negative number, we have to be careful. So when we divide negative 33 division 7, so certainly this quotient is also negative. So it will be negative 33 over 7. It will be negative 4 point something. So it will be in between minus 5 to minus 4. So I cannot take this negative 4, I'll take negative 5. So I'll write this is equal to your 7 into minus 5, that will be minus 35 plus 2. So 2 is the residue here. So when I'll write negative 33 is congruent to, I'll write 2 modulo 7. So the least residue for B is your 2. Now coming to C1, C, find the least residue of 5 modulo 7. 5 when divided by 7. So when 5 divided by 7, it will be, what you will write, 7, 0 times is 7. Sorry, 7 multiplies 0 is 7. This should be plus 5. So the residue is your 5. Your 5 is the residue. So next some example for modulo 3. First is find the least residue of 9 modulo 3. First one. So we know that when 9 is divided by 3, we get 3 as quotient and remainder as 0. So it is simple. So your least residue is 0. Or if you want to write in the modular form, it will be 9 is congruent to 0 modulo 3. Now part 2, it is negative 2, so it is little bit confusing. So take care, because this remainder will not be in negative. Remainder should be, or residue should be always positive, is positive. So we have to make the residue as positive. So what I'll do, I'll write this is equal to negative 2 is equal to 3 into negative 1 plus 1. So this is my remainder. Let me explain again. Negative 2, if I'll divide it by 3, I'll write negative 1, then it will be negative 3, and I'll subtract, it will be 1 is the remainder. So here, the residue will be 1. Now part C, least residue of negative 10 modulo 3. Negative 10 modulo 3. Negative 10 is divided by negative 3. So again what I'll write, negative 10. So you have to take a multiple of negative. So this will be negative 4. It will be higher than that. It will be negative 2. If we subtract, 2 is the residue. 2 is the remainder, or 2 is the residue. So this can be written as minus 10 is equal to 3 into minus 4 plus 2. After, if you have confusion, you can check again. Take this one and subtract this residue, so that this will be divisible by 3. Because a minus b should be divisible by n. You can check once after getting the answer. So this residue is 2 here. Next, least residue of 17 modulo 10. I've taken some example of modulo 10 because this is very important to find your last digit of a number when raised to certain power. It is asked in many competitive examinations. So A is 17 divided by 10. So it is easy. Question is 1 and remainder is 7. So this is your residue. Least residue is 7. So when it is least residue 1, it should be the smallest one. Least residue of negative 1. Negative 1 modulo 10. Then this will be, you have to take a number in a multiple should be negative. So I'll write this will be negative 1 is equal to 10 multiplies negative 1 plus 9. It can be. So 9 is the remainder here. Or you can think of negative 1 divided by 10, negative 1, negative 10, subtract it, it will be 9. So 9 is the remainder here, and so it will be the residue. Now third one, I hope you can try for third one, negative 38 modulo 10. Same thing, 10, 4 times negative 40. 10 into minus 4 is equal to minus 40. So minus 38 is equal to minus 40 plus 2. So 2 is the remainder. So 2 is remainder. And quotient is your minus negative 4. So LR is 2. Let us take another example and find the least residue of 171 plus 169 modulo 17. So we can keep an eye on this property. If A is B A is congruent to B modulo M, C is congruent to D modulo M, then A plus C is congruent to B plus D modulo M. So first I'll get 171 is congruent to what modulo 17. That means 171 division 17, what is the residue or what is the least residue? It will be 1 because 10 is the quotient and 1 is remainder. So this will be 1 modulo 17. Similarly, 169 is congruent to 169 division by 17. I'll write this is 170 minus 1 division 17. So certainly negative 1 is the residue. So this will be negative 1 modulo 70. Now the question is, we can write 169 division 17, 79 times your 153, here 9 minus 3 is 6 and 1. I can write, but I want to write in the least thing, smallest one, so that this calculation will be easier. Then it will be negative 117 minus 6, negative 17. I can also write 16 modulo 17, but I'm preferring this one. Now 171 plus 169 plus 17 is same as 1 modulo 17 minus 1 modulo 17. So minus 1 plus 1 modulo 17, or this will be 0 modulo 17. So the remainder is 0. The residue is 0. Least residue is 0. Now coming to this one, I could have taken this also. It will be same 171 plus 169 modulo 17 is equal to 1 plus 16 modulo 17, that is equal to 17 modulo 17. Certainly the remainder is here 0. So 17 is congruent to 0 modulo 17. So least residue is 0. So certainly this method is more simple to calculate. Another example, 601 minus 6001. Find the least residue of 601 minus 6001 modulo 6. So 601 is congruent to 1 modulo 6, because when I'll divide with 6, certainly the remainder will be 1. And 6001 is also congruent to 1 modulo 6. When you divide with 6, the remainder is again 1. So 601 minus 6001 modulo 6 is same as your 1 minus 1 modulo 6. That will be 0 modulo 6. So 0 is least residue. You can verify it. If we will simplify this, it will be negative 5400. Certainly this is divisible by 6. So remainder is 0. Next is on the property A is congruent to B modulo M, C is congruent to D modulo M, then A product of A C is congruent to product of B D modulo M. So on this property, we'll solve this example. Find the least residue of 17 multiplies 14 modulo M. So if we take 17 is congruent to minus 2 modulo 19. And 14 is congruent to negative 5 modulo 19. Now, when I'll write 17 multiplication 14 modulo 19 is the same as negative 2 multiplies negative 5 modulo 19. So this is equal to 10 modulo 19. 10 modulo 19 is 10 is the remainder, or least residue is 10. Find the least residue of negative 61 and negative 46 modulo 8. Negative 61 is congruent to 3 modulo 8. So the 8 8s are 64 and 61, so this will be 3. Similarly, negative 46 is congruent to 8 6 are 48, so this is 2 modulus 8. So when I'll write negative 61 multiplies negative 46 modulo 8 is nothing but your 3 into 2 modulo 8. So that will be 6 modulo 8. Least residue is 6. Next is power rule for congruences. This is the most important or useful rule for which helps us to simplify many problems asked in the competitive examination and Math Olympiad. If A is congruent to B modulo n and m is positive integer, then A raised to the power m is congruent to B raised to the power n modulo n. So on this basis, we'll first solve a simple question, find the least residue of 19 raised to the power 5 modulo 9. So 19 when divided by 9, we get 2 quotient and 1 is remainder. So 19 is congruent to 1 modulo 9. So 19 raised to the power 5 will be congruent to 1 raised to the power 5 modulo 9. As this said, A is congruent to B modulo n, then A raised to the power n is congruent to B raised to the power m modulo n. So here, this is 19, sorry. A is 19 and B is 1, and this M is your 5. So 1 raised to the 5 is 1 again. So 1 modulo 9, that means 1 is least residue. So you must be excited to solve more problems. 25 raised to the 25 is modulo 6. So let us go for 25. 25 division 6 is again 4 is quotient and 1 is remainder. So 25 is congruent to 1 modulo 6. So 25 raised to the power 25 is congruent to 1 raised to the power 25 modulo 6. 1 raised to the power 25 is again 1. 1 modulo 6. So 1 is least residue. Twenty-five raised to the 25 modulo 13. We have to find the least residue. Now coming to 25 is congruent to, I cannot write the 25 divided by 13 is equal to 1, 13, 12. Because if I take 12 as the residue, that means 12 to the power 25 I have to find out. So what I'll do, I'll write 13, 25, I'll get 2, 26 and the remainder is negative 1. Because negative, when I'll take 25 raised to the power 25, then either it will be, if I'll take this one, it will be 12 to the power 25. If I'll take this one, it will be negative 1 to the power 25. So this will be more simpler. So I'll take this one. So 25 is equal to negative 1 modulo 30. So 25 raised to the power 25 is congruent to negative 1 raised to the power 25 to 13. And you know that negative 1, if it is odd power, then it is negative 1. And if this is even, then you will get positive 1. So this will be negative 1 mod 13. Then is the least residue is negative 1? No, because residue will be written in always positive. So I'll write 13 minus 1, that will be 12 is the least residue. Another example, find the least residue of negative 9 raised to the power 4 modulo 6. So a negative 9 raised to the power 4, this is same meaning as 9 raised to the 4. I'll get modulo 6. So 9, now let us take first 9. 9 is congruent to 3 modulo 6. So 9 divided by 6, the remainder is 3. So when write 9 raised to the power 4 is congruent to, it should be 3 raised to the 4 modulo 6. 3 raised to the 4 is 81. Instead of 81, I am writing 9 to the power 2 modulo 6. Now coming to 9. 9 is congruent to 3 modulo 6. We have already written. So 9 raised to the power 2 is congruent to 3 raised to the power 2 modulo 6. So 3 raised to the power 2 is 9. So 9 modulo 6 is again 3 modulo 6. So least residue is three. Find the least residue of 16 raised to the 9 modulo 3. This is for your practice. Before seeing the answer, you can solve yourself if you are really interested to learn. And if you will learn yourself, solve yourself, you can solve yourself, then my product will be a successful one. So 16 is congruent to 3 modulo 13. So 16 raised to the power 9 is congruent to 3 raised to the power 9 modulo 13. Now let us come to 3 to the power 9. 3 to the power 9 can be written as 3 to the power 3 multiplies 3 to the power 3 multiplies 3 to the power 3. 3 to the power 3 means your 27. So that is equivalent to 1 modulo 13 because 3 raised to the power 13, 3 is 27. 27 is 1 modulo 13. So 3 to the power 9 modulo 13 can be written as 1 multiplies 1 multiplies 1 modulo 13. This is equal to 1 modulo 13. Its residue is 1. Thanks for watching. Like and comment. Please subscribe. Next video will be solving problems related to unit plus digit of any power, applying these congruences and least residue, which is asked in many competitive examinations. This is series 3. So here we'll find last digit of large powers, which is a very common concept in many competitive examinations, including Math Olympiad. For that, we'll learn cyclicity and power cycle of the numbers, and we'll find the unit digit of large powers using that. So what is unit place digit? Unit place digit is the least residue modulo 10. That means, suppose I'm taking 2 raised to the power 7. What will be the result? Result is 2 to the power 7 is equal to 2 to the 5 is 32, 60 power 128. So what is its unit place digit? Its unit place digit is 8. How I'll know? This is same as when I am dividing with 10, the remainder 8 is unit place digit. So this is the given that unit place digit is least residue of modulo 10. Now for other big powers, we'll apply this one. If A is congruent to B modulo 10, then A raised to the power n is congruent to B raised to the power 10 modulo 10. So gradually when I'll come across the questions, I'll explain this. But for the time being, I'm finding what is the cyclicity of the numbers. For example, 2 raised to the power 30, 30. So what will be the result here? I'm not asking about the result, but I am interested in the unit place digit. So for this, we'll go or we'll learn the cyclicity of the numbers and power cycle of the numbers. So this is a table you can note down. For number 1, for number 1, it has only one cyclicity and power cycle is 1. What does it mean? If I'll take 1 power 2, this is 1. 1 power 3 is also 1. 1 power 4 is also 1. That means any power I'm getting 1. So this 1 is coming all the time. So its cyclicity is 1. And the power cycle means this is the value that is 1. So what does it mean? If I take 1 or 21 raised to the power 34, when I'll take the thing. So 1 raised to the power any power is, the end will be always 1. This is the meaning of this. Similarly, coming to 5. So 1 we got, then 5 has also cyclicity 1. I'm going from simple to complex. 5 has 1 and its cycle power is 1. That means 5 raised power 1 is 5. 5 power 2 is 25. So end is 5 again. So unit place digit is 5. 5 to the power 3 is equal to 125. So end is again 5. So it is a cycle power cycle is 5 and it is cyclicity 1. Only one value is repeated. Now coming to 6. 6 also same. 6 raised to the power 1 is 6. 6 raised to the power 2 is 36. The unit place digit is 6. 6 power cube is 216. So again 6. So this is the thing. Now same as your 0. If the end result is 0 to the power anything, it ends in 0. Suppose 20, its square is, it ends in 0. This is the meaning. So till we finish the session, you may not be grasp all the things, but have patience and try to finish the session or go through very patiently. I am sure you will learn all the things. So we have finished 1, 5, 6 and 0. Now coming to, I am taking the cyclicity 2, it is 4. It is cyclicity 2, 4 and 6. What does it mean? 4 power 1 is 4. 4 power 2 is 16. So the unit place digit is 16. 4 power 3 is equal to 64. So again 4. 4 to the power 4 is 256. So again it is 6. So there are two power cycle. One is 4 and 6. 4, 6. 4, 6. So it go on repeating. And cyclicity is 2. That means 2 is repeated. 4, 6, 4, 6, 4, 6, so on. Similarly, another two cyclicity is your 9. 9 power 1 is 9. 9 power 2 is 81. 9 power 3 is your 729. Again 9. 9 to the power 4 will be 9 times of this. 9, 9, 81 carries 8. 9 2s are 18. 18, 8, 26, 2. 9, 7, 63. 2, 6, 5, 6, 1. So 9, 1, 9, 1. 9, 1, 9, 1. So there are only two power cycle. So it is again, this is also easier one. So next is Next is 3, 2, 3. 2, 3. 2 power 1 is 2. 2 power 2 is 4. 2 power 3 is 8. 2 power 4 is 16. So and is 6. 2 raised to the 5 is 32. It again 2. 2 to the power 5 is 32. 2. 2 to the power 6 is 64. 4. So this is a cycle till this 2, 4, 8, 6. Again 2, 4, 8, 6. 2, 4, 8, 6. So we say there are 4 power cycles. and its cyclicity is 4. So you have to keep in mind so that you can solve the problem easily. Similarly, coming to 3, 3 power 1 is 3, 3 power 2 is 9, 3 power 3 is 27, so end is 7, 3 to the power 4 is 81, 3 to the power 5 is 243. So again 3 is repeated. Again if I 3 to the power 6 will be 729. So it is repeated. So its cyclicity is 3971. 3971, 3971, so on. So the cyclicity is 4. After 4 it is repeating. So last is your 7 and 8. So next is for 7. It has cycle 4. Why? 7 power 1 is 7. 7 power 2 is 49. 7 power 3 is 343. 7 power 4 is equal to, you will multiply 3 again, 7 again, 2401. Again if I'll multiply again another 7, it will be 7 to the power 5, which will be 172, 168, 07. So again 7 is repeated. So its cycle is 7, 9, 3, 1. After 4 it will repeat again, and the number of cycle is 4. Power cycle, this one. Coming to 8. 8 power 1 is 8. 8 power 2 is 64. That means end in 4. 8 power 3 is equal to 512, and in 2. Then 8 to the power 4 is equal to 4096. So 6. So its power is 8, 4, 2, 6. Again 8, 4, 2, 6. So gradually while solving we can remember this, where we can also calculate. So this is a problem, sample problem. What is the last digit of 2001 raised to the power 2005? 2001, the unit place digit is 1. It is understood. That means this is same as 2001 is congruent to 1 modulo 10. That means this is the least residue. Using least residue, I am making the number smaller. This is the magic of number theory or your congruences. We can make the calculation smaller. Now 2001 to the power 2005 is congruent to 1 raised to the power 2005 modulo 10. Now we'll go for the cyclicity of 1. 1 cyclicity is 1. That means 1, any power is equal to 1. So I'll write this is congruent to 1 modulo 10. That means if the number is divided by 10, the residue will be 1. Then unit place digit is 1. So have patience till you finish this video, whole video. You may not be able to solve all the questions. So try to comprehend. Next is what is the last digit of 2 raised to the power? 2017. So for this, let us see the cyclicity. It is 4. That means after 4 it will repeat. So it will go on. 2 to the power 1 is 2. 2 to the power 2 is 4. 2 to the power 3 is equal to 8. 2 to the power 4 is 16. So last is 6. Again 2 to the power 5 is 32. So this is 2. That means 2, 4, 6, 8, 6. Again 2, 4, 8, 6. So on. That means if it will complete 4 cycle or 4 completed, then it will end in 6. So now let us see 2017 can be written as, I'll see how many cycle it will complete. So I'll divide by 4. 504 is the quotient and remainder is your 1. So 2017, 2 raised to the power 2017 can be written as 2 raised to the power 16 into 2 to the power 1. 2 to the power 16 is 4 times of 504. That means 4 cycle it is completing and 2 is here. So I'll take the modulus now, modulo 10 now. So 2 raised to the power 4 into 504 into 2 modulo 10 is equal to congruent to, now see this one, it is completing cycle of 4. So when completing cycle of 4, the end is 6. So it will be 6 multiplies this 2 modulo 10. 6 multiplies 2 is 12. So 12 modulo 10, that means when I divide 12 with 10, I get result is 2. So 2 modulo 10. When 2 modulo 10, that means 2 is the remainder. 2 is the unit place digit. Next, what is the last digit of 3012 raised to the power 2056? So first I'll convert this base into modulo 2 to find its unit place digit. It is 2, it is visible. So 3012 is congruent to 2 modulo 10. So 3012 to the power 2056 is again congruent to 2 raised to the power 2056 modulo 10. So this question now converted to or changed to 2 raised to the power 2056. After converting to a simpler form or smaller, first next I'll get the 2 cyclicity. Again we have repeated just now. 2, 4, 8, 6. So I'll see whether it is multiple of 4 or not. If it is multiple of 4, then the result is 6. So 2056, if we divide it with 4, it will be 5, 14, yes. So 2 into 4 into 5, 1, 6, 4 modulo 10 is equal to 6. Gives the result 6 modulo 10. 6 is unit place digit. Find the unit place digit of 145 raised to the power 502. So 145 is congruent to 5 modulo 10. So 145 raised to the power 502 is congruent to 5 raised to the power 505 to modulo 10. And next see the cycle of 5. 5, any power is always ends in 5. This will be 5 modulo 10. So the unit place digit is 5. Find the unit digit of 6 raised to the power 2025. Is it very easy? 6 power anything is ends in 6. 6 power anything ends in 6. So it ends in 6. Our unit place digit is 6. After solving some questions, you will find that it's not that difficult. Next is find the unit place digit of 2014 raised to the power 2013. So 2014 modulo 10 is nothing but your 4 modulo 10. 2014 raised to the power 2013 modulo 10. Once you understood, you can, without writing all the steps, you can find the shortcut way also. It will be 4 to the power 2013 modulo 10. Now we'll go for cycle of 4. 4 is 2 only, 4 and 6. 4 power 1 is 4. 4 power 2 is 16 ends in 6. Again 4 power 3 ends in 4. 4 to the power 4 ends in 2, 5, 6. So you can make a conclusion here. If the power is odd, we are getting 4. If power is even, we are getting 6. So 2013 is a odd number. So we'll get 6. So 4 raised to the power 2013 mod 10 is equal to 4 mod 10. Since it is an odd number, it ends in 4. If it is an even number, it ends in 6. So the unit place digit is 4. Next, find the unit place digit of 444 raised to the power 444. So 444 modulo 10 is congruent to 4 modulo 10. Now 4 to the power 444 is same as congruent to 4 raised to the power 444 modulo 10. Now same concept, this 444 is your even number. So 4 raised to the power 444 modulo 10 will be congruent to 6 modulo 10, or it ends in 6. At place digit is 6. Next is 1989 to the power 1989. So let us write 1989. It is congruent to 9 modulo 10. So this is congruent to 9 to the power 1989 modulo. Now let us check the 9 cycle. 9 raised to the power 1 is 9. 9 raised to the power 2 ends in 1. 9 to the power 3 ends in again 9. That means if it is odd, power is odd, then ends in 9. If power is even, ends in 1. So 1989 is odd number. So this ends in odd number, ends in 9. So 1989 is congruent to 9 modulo 10. So 9 is unit place digit. So what is the last digit of 3 raised to the power 2012? So we have to see the cyclicity of this 3. 3 is 4. After 4 it is repeated 3, 9, 7, 1. 3 raised to the power 1 is 3. Then your 9. Then ends in 27, 7. Then 3 raised to the 4 is 81, ends in 1. 3, 9, 27, 81. Again 3 to the 5 is 243. So it go on increasing. That means repeating this things 3, 9, 7, 1. So we'll see how many 4 cycles it is completing. How many cycles? 4 times. So 2012, if we divide by 4, it is completely divisible. So 503. So when it is completing 4, the end is 1. 1, 2, 3, 4. The end is 1. So its unit place digit will be 1. So I will write 3 raised to the power 2012 is congruent to 3 raised to the power 4 into 503. This is congruent to 1 modulo 10. So remainder is, or unit place digit is, or last place digit is 1. Same question, if it would be 3 raised to the power 2013, then what would be the answer? It will be 3. So that time you must write 3 raised to the power 2012 into 3 power 1. So this is congruent to, this gives you 1 and multiply 3 modulo 3. Modulo 10, sorry. So this is 3 modulo 10 means unit place digit would be 3. Similarly, if it would be 3 to the power 2014, then it will be your 9, because 3 to the power 2. 3 to the power 2 is 9. 1 multiply 9. It will be 3 raised to the power 2012 into 3 to the power 2. That is 24. So this will be 1 multiply your 9. So 9 modulo 10 is, answer is 9. 9 would be the result. What is the last digit of 1453 to the power 71? So we'll write 1453. First we are taking the unit place digit, this is congruent to 3 modulo 10. And if it is power 71, this will be power 71. So now 3 raised to the power 71 modulo 10, when we'll calculate, this is, we'll see how many cycles it will complete. How to get it? 71 divided by 4. So how much we are getting? 71 divided by 4. It will be 17. Quotient is 17 and remainder is 3. That means 3 to the power 71 will write as 3 to the power 68 into 3 to the power 3. 3 to the power 68 means 3 into 4 into 17, which will gives you 1, and 3 to the power 3 is 27. So now we'll go for the modulo 10. So it will be 1 into 27 modulo 10. 27 modulo 10 is your 7. So 7 is the unit place digit. Last digit of 17 raised to the power 17. 17 raised to the power 17. 17 is congruent to 7 modulo 10. Now when I'll write 17 to the power 17 is equal to 7 raised to the power 17 modulo 10. Now coming to 7 to the power 17, we'll compare with from the cycle. It is 4 cycle, 7, 9, 3, 1. Again 7, 9, 3, 1. So if it is 4 multiple, then it will be 1 as your 3. So if it is 3 to the 17 means 7 raised to the power 16 into 7, 7 to the 1. So when it is 7 raised to the 16, then it will end in 1. So this will be congruent to 1 into 7 modulo 10. So this is same as 7 modulo 10. So 7 is the unit place digit. Next question, it's sometimes asked in MBA entrance examination also. Last digit of 2 raised to the power 16 to the raised to the power 2015 minus 2015 raised to the power 2016. So it is, the number is so big, but you can see how much time will take to solve it. It will be done in 1 minute only. So 2016, this was 2015, that's end is 6. This is same as 6 raised to the power 2015. And this number always ends in 6. Any power ends in 6. I'm talking about the last digit. We are not calculating the whole thing. Only we are interested for last digit. Similarly, this is 5. 5 raised to the power 2016. Again, 5, any power, it is always ends in 5. So this result will be 6 minus 5 is 1. Now there is a self-evaluation question. You can solve it yourself so that you can understand how much you have grasped. So subscribe the channel, like the videos, and share and comment. Comment your answer in the message section. Thank you for watching. Thank you for watching whole video. So next video, we'll be learning about Fermat's little theorem, how it is applied in more complex powers. Thank you. Fermat's little theorem, how it can be applied in solving problems. So let's begin. We'll see many solved examples. Fermat little theorem says let P be a prime number and let A be an integer that is not a multiple of P. That means P and A are co-prime. Then only we can apply the Fermat's little theorem. P should be a prime number and P and A are co-prime. Then we can write A raised to the power P minus 1 is congruent to 1 modulo P. Or it can be written as A raised to the power P is congruent to A modulo P. Let us take some example, or let us verify first. A is 3, P is 5, so P is a prime number. A and P are co-prime, then we can apply this. Let us verify that this theorem 3 raised to the power 5, we know that it is 243, and according to this little theorem, it should be 3 raised to the power 5 must be equal to 3 modulo 5. So 3 raised to the power 5 is equal to 243. So if we divide 243 with 5, certainly the remainder is 3. 243 divided by 5 is your remainder is 3. So hence it is verified, and after the verification it is easy to convince. I am not going to prove this theorem because it is not that much needed for our purpose. So the example is 3 raised to the power 6 is congruent to 1 modulo 7. So 7 is a prime number and 3 and 7 are co-prime, so we can apply. So 3 raised to the 6, we can write 3 raised to the 6 is congruent to 1 modulo 7. That means when 3 raised to the 7 is divided, 6 is divided by 7, we get the residue 1. Another example, 13 raised to the 16 is congruent to 1 modulo 17. 17 is a prime number, 13 and 17 are co-prime, then we can take this result 13 raised to the power 16 is congruent to 1 modulo 17. Another example, 9 raised to the power 10 is congruent to 1 modulo 11. 11 is a prime number and 9 and 11 are co-prime. Then we can write 9 raised to the 10 is 1 modulo 11. So Fermat little theorem is applicable on this condition, and it can be applied to a bigger base. So where this previous knowledge is not applicable or difficult or lengthy, then only we apply this shortcut method. So let us solve some examples or questions. Find the least residue 4 raised to the power 20 modulo 7. So applying this theorem, A raised to the power P minus 1 is equal to 1 modulo P. I can write 4 raised to the power 6 is congruent to 1 modulo 7. 7 is a prime number and 4, 7 are co-prime. So we can write 4 raised to the power 6 is equal to this. Now coming to 20. 20 we have to express in terms of your 6. So 20 can be written as your 6 into multiplies 3 plus 2, 18 plus 2. So 4 to the power 6 is 4 to the power 4 to the power 20 can be written as 4 raised to the power 26 into 3 into 4 to the power 2. So this gives 1 modulo 7. So this is congruent to 16, 4 raised to the power 16, 16 modulo 7. So 16 divided by 7 gives us your remainder 2. So this is same as 2 modulo 7. So 2 is least residue or the remainder. Next, find the remainder when 3 raised to the power 88,888 is divided by 5. So 5 is P here and this is 3 is A. They are co-prime. So I can write A raised to the power 3 raised to the power 5 minus 1, 4 is congruent to 1 modulo 5. So 3 raised to the power 4, power any number is again your congruent to 1 modulo 5. So 8, 8, 8, 5, 8 is such a big number, but it is divisible by 4. So 4 times of 2, 2, 2, 2, 2. So I can write 3 raised to the power 8, 8, 8, 8 is same as 3 to the power 4 into 2, 2, 2, 2, 2. So this will be congruent to 1 modulo 5. So the remainder is 1. Next, find the remainder when 9 raised to the power 1990 is divided by 11. So 11 is prime number. 9 and 11 are co-prime. So I can write 9 raised to the power 10 is congruent to 1 modulo 11. That means when 9 raised to the 10 is divided by 11, we get the residue 1. So we'll now write 1990 in terms of 10. So this will be 10 into 199. So this is congruent to 1 raised to the power 199 modulo 11. It will be 1 modulo 11. So 1 is a remainder. Find the remainder of 2 raised to the power 1000 when it is divided by 13. So 13 is a prime number. 2 and 13 are co-prime. So we can apply Hermit's little theorem. So I can write 2 raised to the power 12 is congruent to 1 modulo 13. That means when 2 raised to the 12 is divided by 13, we get the remainder 1. So next is to convert this or to write this 1000 in terms of 12. So 1000 is equal to 12 into 83 plus 4. Divide 1000 with 12. You get 12 8 times 96. 40, 12 3 times 36. We're getting 4. So that means this is your 12 3 times 36 carries 3. 12 8 is our, or this will be 966. 996 plus 4. So I may write 2 raised to the power 1000 is equal to 2 raised to the power 996 into 2 to the power 4. 2 to the power 996 is 2 to the power 12 to the power your 83. Thus will be congruent to 1 raised to the power 83 modulo 13. So 2 raised to the power 1000 can be written as 1. Here it will be 16 modulo 13. Because 1 raised to the 83 is again 1. Now 16 modulo 13 means when you will divide 16 with 13, we get remainder is 3. So here the answer is your 3. So remainder is 3. Next, find the remainder when 128 raised to the power 129 is divided by 17. So 17 is a prime number, 128 and 17 are co-prime. So we can apply this theorem. I can write 128 raised to the power 16 p minus 1 is congruent to 1 modulo 17. Now to write 129 in terms of 16, 129 is equal to 16 into 8 plus 1. So 128 to the power 128 into 128 is congruent to 1 raised to the power 128 is again 1. So 128 modulo 17. So when 128 divided by 17, 17 7 times 109, we get 9 is the remainder. So this is congruent to 9 modulo 17. So 9 is the remainder. So you can practice some more questions so that you can be perfect. I'd like to introduce another new function, that is Euler's phi function, and how this phi function or torsion function is used in number theory. So what is Euler's phi function? Euler's phi function is also called Euler's torsion function. It is a function that gives us the number of positive integers less or equal to a given number integer n. Those are co-prime to n. It is usually denoted by Greek letter phi, phi. Phi of n is the symbol to represent phi function. Let's see how to calculate phi of n. Phi of n for an input n is the count of numbers in set 1, 2, 3 up to n minus 1. Those are relatively prime to n. Or phi of n count the numbers whose GCD, greatest common divisor, with n is 1 and the number is less than or equal to n. So let us find one by one. First is phi of 1. Phi of 1 is 1 because GCD of 1 and 1 is 1. We don't take count 0. Phi of 2. Phi of 2 is also 1. Why? GCD of 1 and 2, if we take 2, that means 1 and 2. So phi of 1, GCD of 1 and 2 is 1, so that is one count. And GCD of 2 and 2 is 2, it is not counted. So only 1 is counted here, so phi of 2 is 1. Next is phi of 3. Phi of 3 means we'll take 1, 2, 3. So 1 with 3, they are co-prime. So that is 1. Then 2 and 3 is another one, but 3 and 3, GCD is not 1. So it is not considered. So there are two counts. Here 1, here 1. Or we can take 1, 2 are counted. This is 1, this is 1, 2. Phi of 4. Phi of 4 is 1, 2, 3, 4. So 1 and 4, they are co-prime. So 1 is counted. 2 and 4, 2 is not counted. 3 and 4, again it is counted. So it is 3 and 4 is 1. So it will be phi of 4 is 2. Phi of 5. Phi of 5 is 1, 2, 3, 4, 5. 1 and 5 co-prime, so it is counted. 2 and 5 also counted. 3 and 5 also counted. 4 and 5 also counted. And 5 of 5 is not counted. So 1, 2, 3, 4 are counted. This is 4. Next is phi of 6. 1, 2, 3, 4, 5, 6. So 1, 6, the GCD is 1, yes. 2, 6, GCD is not 1, so it is not counted. 3 and 6, GCD is not 1, not counted. 4 and 6, not counted. But 5 and 6 are counted. So GCD, phi of 6 is 2. So what will be phi of 7? You can calculate. So these are the phi of some numbers from 1 to 21. You can pause or you can calculate yourself. You can verify whether you are correct or not. But is it possible to find all the phi of n, all the numbers? So there should be some shortcuts or theorems or rules. So let us go one by one. One is theorems related to Euler-Euler's phi function. If p is prime, then phi of prime p equals to p minus 1. That means no need of counting. We can simply write down because 1, 2, 3 up to p minus 1 are all relatively prime to p. But 0 is not considered. For example, we had already found that uh, phi of 3 1, 2, 3. This will be your 1, 3. GCD is 1, 2, 3. GCD is 1. So there was 2. So here this is a prime number. You can directly write 3 minus 1, that is equal to 2. So examples, phi of 5 will be 5 minus 1, 4. Phi of 13 will be 30. This is a prime number, so it will be 13 minus 1 is 12. Phi of 29, this is again a prime number, so we can directly write 29 minus 1 equals to 28. So this is one rule or one theorem. When p is prime, we can phi of prime we can write just minus 1. Now second theorem, if a and b are relatively prime and n equals to product of a and b, then we can write phi of n equal to phi of a multiplies phi of b. For example, if I write phi of 12, phi of 12 is same as your phi of 3 multiplies phi of 4 because 3 and 4 are prime to each other. So let us see some examples. One is phi of 35 can be written as 7 into 5, they are prime to each other, co-prime. So it can be 5 into 7, 5 of 5, 5 of 7. Multiplication, phi of 5 again can be put into formula, that is the prime number. I can write 5 minus 1, and phi of 7 again prime number. I can write 7 minus 1, 6. So it will be 4 multiplied 6, that will be 24. Let us take another example. Phi of 15, it can be written as 3 multiplication 5. 3 is prime, 5 is also prime, and they are co-prime. So we can put this um, rule. That will be 3 minus 1, 2, 5 minus 1, 4, that is 8. Similarly, phi of 21 can be written as 5 into 3, product of 7. So phi of 3 into 5 of 7, that will be 12. So bigger numbers can be written or arranged in this way. Next is, if p is a prime and n is a positive integer, then phi of p power n equals to p power n minus p power n minus 1. So phi of 2 to the power 5 can be written as 2 to the power 5 minus 2 to the power 4. Phi of 2 to the power p is a prime number. I have taken p is a prime number, 2 prime number. N is any positive number, then it can be written as t to the power 5 minus 2 to the power 4, or 532 equals to your 2 to the power 5 is equal to 32 minus 16, that will be 16. So this is the example we have done. So another is phi of 125. 125 can be written as 5 power 3. So both are co-prime to each other. So I can write 5 power 3 minus 5 to the power 2. That will be 125 minus 25 equal to 100. So next is another theorem. For bigger numbers or complicated numbers, we can use this one. If n is a positive integer with prime factorization of factors p1 power n1, p2 power n2, pk power nk up to, then phi of n can be written as individually this one, this one, this one. So it will be p1 n1 minus p1 n1 minus 1. Individually I am writing for all p2 power n2 minus p2 power n2 minus 1 up to pk to the power nk minus pk nk minus 1. That means this is same as your phi of p1 n1 multiply phi of p2 n2, phi of p3 and 3, so on up to pk and k. Again, it can be individually written in this form, 2 to form. Or this is a very useful simplification or derived formula from this. If I take n common, or we can write this thing in this way, phi of n equals to n into 1 minus 1 over p1, 1 minus 1 over p2, 1 minus p over 1, 3, so on. So this is the easier than, simpler than this formula. This is same as derived formula. You can find, or most of the times we use this formula. So let us take some example. For example, 120 can be written as 2 power 3, 8 into 3 into 5. That means here P1 is your 2, P2 is 3, and P3 is 5. Here N1 is 3, N2 is 1, and 3 is 1. So when I'll write phi of 120, it will be n is 120 multiplies 1 minus P1, 1 over P1, that means 1 minus P1, here it will be 2, not power 3, 2. Similarly, second one will be 1 minus 1 by 3, this is P2, and 1 minus 1 by 5, that will be your P3. So this is simple. So it will be 120 multiplies 1 and minus half is 1 by 2. 1 minus 1 by 3 is 2 by 3, and this is your 4 by 5. You will simplify. This will be 5 to the 10, 3, 4. Then it will be 4, 4, 16 to 32. So let us find ourselves. Find phi of 92. So I can make the 92 as a factor. 92 is 2 multiplies 2, 4 multiplies 23. So this will be 2 power 2 into 23. So that there are only P1, P2. So phi of 92 equals to 92, that is n, multiplies 1 minus P1, that is 2, multiplies 1 minus P2 equal to 1 over 23. So this is equal to 92 multiplies 1 by 2 multiplies 22 over 23. So 23, 4, 2 is 11. So the answer is 44. So phi of 92 equals to 44. So next is find phi of 100. So let's find. We'll write the factorization of 100. It is 2 multiplies 2 multiplies 5 multiplies 5. Or this is 2 power 2 and 5 power 2. So there are only two factors, P1, P2. So phi of 100 equals to 100 multiplies 1 minus P1, here 1 by 2, multiplies 1 minus 1 by 5. So please note that it is nothing to do with the powers, only the factor we are writing here or the prime factors. So this will be 100 multiplies 1 by 2 over 4 by 5. So 2 5s are 10, I'll cancel, so this is 40. So phi of 100 is 40. So this is a very important result for us because many things will solve in number theory using this fact. As I told, we will use this in number theory. So now, after learning the calculation of phi of a number, then how it is used in number theory. So in a nutshell, we learned that Euler's phi function, phi of n, is the number of integers m belongs to 1 to n with m co-prime to n. Now how it is used in number theory? If a is a co-prime to n, then a power phi of n is congruent to 1 modulo n. This is our applications in number theory. A of any number co-prime to n can be written as a power phi of n is congruent to 1 modulo n. That means a power phi n, when divided by n, we get 1 as a remainder. So let us verify. So I have taken 2 phi of 7 is congruent to 1 modulo 7. Let us see. So first I'll calculate phi of 7. We know that 7 is a prime number. So when it is a prime number, phi of p equals to p minus 1. So this will be 7 minus 1, 6. So 2 power 6 is your left side equals to your 64. Now 64 is congruent to 1 modulo 7, right? Because when 64 is divided by 7, we get 1 remainder. So it is correct. So we can apply this concept now. We can take very small. So The question is find last two digits of 9 power 201. We have to find the last two digits. That means we have to find the remainder when 9 power 201 is divided by 100. So if we correlate with this phi function, that means we can write the concept here 9, which is a here, because let me write once this theorem, a to the power phi n is congruent to 1 modulo n. Here our n is 100 because we are dividing with 100, and a is 9. 9 and 100 are co-prime, so I can use this here function here. So I can write 9 phi of 100 is congruent to 1 to the 100. That means when 9 power 500 is divided by 100, we get the remainder 1. Now let us find what is the 500. We have already calculated phi of 100. Phi of 100 equals to your 100 multiplies 1 minus half, because 2 is a factor, 1 minus 1 by 5, 5 is a factor, this was 40. Just now we calculated. So 9 power 40 is congruent to 1 modulo 100. So 9 power 201, I'll write this in term of your 9 power 40. So it can be written as 940 multiplies 5, that will be your 200, and another 9 power 1. So this is congruent to, this leaves remainder your 1, because 940 power 5, 9 to the power 40 power 5 to 9 is congruent to 9 multiplies 1 modulo 100. So because 1 power 5 is 100, 1 power 5 is also 1. So the remainder is 09. So when 9 power 2001 is divided by 100, we get 09 as the remainder. So 09 are the last two digits. Let us take another one example. 7 power 2002. Last two digit I have to find. So I'll divide with 100 and find the remainder. So 7 and 100 are co-prime, or GCD is 1. So I can apply this function, phi function here. So phi of 100 equals to 40. We have already calculated. No need of writing again and again. So 7 power 40 is congruent to 1 modulo 100. 2002 will convert in term of 40. So 2002, 2002 can be written as 40 multiplies 50 plus 2. So I need a multiple of 40. So 7 power 40 into 50 into 7 power 2 is congruent to, this is 1 power 50 modulo 100. First one, let me rub this here. So that is same as your 1 modulo 100. When I'll write 7,000, 2022, it can be written as 740 into 50 multiply 7 power 2. So it will be 1 into 49 modulo 10. That will be 49 modulo 100. So it is 49. Last two digits are 4 and 9. So next is find last two digits of 2 power 1997. So I can't apply this phi function directly for 2 and 100 because 2 and 100 are not co-prime. So we can go in another way. We can find the 100 can be written as 4 and 25. So once I'll find modulo 4, once I find modulo 25, then we will calculate. Or you can calculate by other method what I have discussed in other videos. Number theory is also has very important use in cryptography. So we'll learn what is Chinese remainder theorem and how we can solve the Olympiad math problem using this theorem. So let's begin. What is Chinese remainder theorem? If in a set of equations, each equation has a different number, say n1, n2 up to nr, and these numbers are all relatively prime to each other and also have some numbers, say a1, a2, a up to a3 up to ar, then there is a unique solution of this all these equations, that is, if we call it x, that satisfies all the equations at once. This is the definition of remainder theorem. Now, now let's state this theorem mathematically or analyze it. Let n1, n2, n3 up to nr belongs to n natural number system be pairwise relatively prime. First condition is they should be relatively prime. For any a1, a2, a3 up to ar belongs to integer, the solution set of the system of simultaneous equation congruences, if there are many congruence statements, x is congruent to a1 modulo n1, same x is congruent to a2 modulo n2, x is congruent to a3 modulo n3 up to x is congruent to ar modulo nr, then we can solve this problem, or we can find x as it consists of unique congruence class modulo n, where n is the product of all small n1, n2 up to nr. Or this x is calculated by this formula. This is summation of ai multiplies ni multiplies xi, and the sum of all this product starting from 1 to n is equal to 1 to r. How ni is calculated? Capital Ni is calculated by n, which is a product of n1, n2 up to nr, by individual ni. And how xi is calculated? It is your ni xi is equal to congruent to 1 modulo ni. So it seems to be difficult, but when we go for the problem we solve, it is not that difficult. So let us proceed to a example. So I have taken an example of x, as I have taken three equations simultaneous congruences, and we will write the algorithm or steps of how we will find out so that it will be easier for you. The three simultaneous congruences are given as x is congruent to a1 modulo n1, x is again congruent to a2 modulo n2, x is congruent to a3 modulo n3, we'll find x. So step 1, first we'll multiply just n1, n2 and n3. That is denoted as capital N, because at last we'll find x as 1 modulo n. So step 2, then we'll find capital N for each cases, and the formula will follow that n1 is equal to capital N upon small n1, n2 is capital N upon small n2, or capital N3 is equal to small n3. That means ultimately n1 equals to your n2 into n3, n2 is equal to n1 into n3, and n3 equals to your n1 into n2, because n is equal to product of this. Step 3, you will find value of x1, value of x2, value of x3 with three equations. N x1 is equal congruent to 1 modulo n1, n2 x2 is congruent to 1 modulo n2. This step is very important, and n3 x3 is congruent to 1 modulo n3. Now, after getting x1 and x2, x3, as I told, this step is important and this step is slightly critical. Now, step 4 will get all the sum of a and x, that is nothing but your a1 n1 x1, a2 n2 x2, a3 n3 x3 modulo n. So let us go to an example. So there is a question: solve the system of congruences x1, x is congruent to 1 modulo 3, x is congruent to 2 modulo 5, x is congruent to 3 modulo 7. We have to find x. So solve system of congruence means find x. So first we'll check that whether this n1, n2, n3, they are co-prime or not. That means we have to see pairwise that 3, 5, 1, 5, 7 and 3, 7 are co-prime pairwise. That means I can apply the remainder theorem. So now identifying what will be A1. A1 equals to 1, A2, 2, A3, 3, N1, 3, N2, 5, N3, 7. This is your N1, N2, N3. The next is to find out N. N equals to N1, N2, N3. So here if we multiply 3 plus 5 plus 7 equal to 105. So first step is complete. Next, coming to second step. Second step is finding individual capital N. So Ni N1 equal to N by small n1. So it will be 105 by 3. That will be 35. or directly we can multiply 7 and 5. Similarly, n2 equals to n by n2 equal to 105 over 5. This is n2. It will be 21, and n3 equals to 105 by 7. That will be your 15. So I'm writing n now, n individual, that is 35, 21, and 15. So second step is complete. Then coming to third step. Third step is your n1 x1 is congruent to 1 modular small n1. That means applying here, I'll get 35x1 is congruent to 1 modular 3, because n1 is 3. So this step you have to find out. That means think critically. What does it mean? I have to think of what should be the x1 so that product with 35, when it is divided 3, it leaves remainder 1. Repeat, x1 will be by trial method. I'll think of what is the value that when it will be multiplied with 35 and divided with 3, I'll get a remainder 1. So it will be 35 multiplied by 1. It does not leave remainder 1 when divides with 3. But if I'll multiply 2, 35 2 times is 70. So 70 when divides with 3, it leaves 1 remainder. So this implies that x1 is equals to here 2. So I am making table here x, it is 2, first one is 2. Next, in the same way, going for n2 x2 is congruent to your 1 modulo n2. So it implies that your 21 x2 is congruent to 1 modulo 5. So starting from 1, 21 into 1, 21. When it divides with 5, it leaves remainder 1. That means x2 equals to 1. And for x3, n3 x3 is congruent to 1 modulo n3. That means your n3 is 15. 15 x3 is congruent to 1 modulo 7. So it's also easy to find out. 15 into 1 multiply 1. When divides with 7, it leaves remainder 1. So x3 is also 1. So 2, 1, 1. Then what to find? X. X is equal to summation of your A1, N1, X1 plus A2, N2, X2 plus A3, N3, X3 whole modulo N. So let us multiply all the things. That means I'll multiply A1, X1, N1, X1. So X is congruent to, not equal to, congruent to 135 into 2 plus A2 and 2 X2. 2 into 5 into 1 plus A3 3, 15 and 1. It's not, sorry, it is not N2. I made a blunder here. It will be 21 only. It is your 3 into 15 into 1. I'm sorry. So whole modulo, and n is how much? N is equal to 105. So x is equal to, this is 70 plus 42 plus 45 so 105. So if we take the sum, how much it is? It is your 157 below 105. That means if we divide 157 with 105, what is the remainder? Remainder is your 157 divided by 105. 52 is the remainder. So 52 is the answer here. X equals to 52. So solution is x is equal to 52. I hope it's easy for you. Now you feel easy. Next question. Next question, I have taken only two components, not three. So x is congruent to 3 modulo n. X is congruent to 9 modulo 13. That means a1 is equals to your 3, a2 is 7, and n1 is 9, n2 is 13. And you will see that 9 and 13 are co-prime. So I can use this remainder theorem. So first I'll get n. N is equal to n1 into n2. That will be 117. Next I'll get individual n. That will be, so it is, obviously it will be 117 by 9. That will be 13. N1 will be 13 and n2 equals to 9. When two are there, it is easy. Now coming to x1, x2. x1, n1, x1 equal to your 1 modulo n1. That means 13 x1 is congruent to 1 modulo your 9. 13x1 is 1 modulo 9. Then how to find out? Just let's think. It will be 13. 1 is 13. 26 no. 39 no. 52 no. 65 no. 37, 36 times 78 no. 13 7 91, that time it will be. So that means x1 is your 7, because 13 7 is 91. When it divides your with 9, it leaves one remainder. Next is n2 x2 is congruent to 1 modulo n2. That means your 9x2 is congruent to 1 modulo 13. So 9, 2 times 18, 3 times 27. Yes, 27 gives us 27 when divides with 13 we get remainder 1. So it will be 3. 9 3 times 27. So x2 is equal to 3. So 7 and 3. Now I'll multiply a1 and 1 this. So x equals to 3 into 13 into 7 plus 7 into 9 into 3 modulo what is n? N is equal to 117. So x is equal to, now if we multiply it will be 273 plus 3 9 21, 289, 189, 117. So if we'll add this equals to your 462 modulo 117. When 462 is divided by 117, divided with 4 or 3, 3. It will be 351, 111. So 111 is the remainder. So the solution is 111. Now a question, a number when is divided by 3 leaves remainder 2, when divided by 4 leaves remainder 3, and when divided by 5 leaves remainder 4. What's the number? So it is given in the word problem. So we'll frame the equations. We'll write let the number be x, and x is congruent to 2 modulo 3. That means when it is divided by 3 leaves remainder 2. Same when it is divided by 4 leaves remainder 3, and when divided by 5 leaves remainder 4. So there are three equations, three congruences, not equations. We have to find x. Since 3, 4, 4, 5 and 3, 5 are pairwise prime, we can apply Chinese remainder theorem. First we have to mention why we are applying this one. Next, after the framing equation, we'll write your what is a1. A1 is 3, a2, then a2 is 3, then a3 is 4. And what about n1? N is 3, 4, 5. First I'll go to step 1. I'll find n. N is equal to your 3 into 4 into 5. That will be 60. Now getting n individual, n1 will be certainly 60 divided by 3, it will be 20, n2 equals to 60 divided by 4, that will be your 15, and n2 is equals to 60 divided by 5, that will be 12. This will be 20, 15, 12. After getting n1, n2, n3, second step is complete. Then we'll go to third step. That will be n1, x1 is congruent to your 1 modulo n1, or I'll write your 20x1 is congruent to 1 3. Now if we'll go on calculating, 21 into 1, 20, when divides 3, does not leave remainder 1. Then I'll go for 2. 20 multiplies 2 is 40. When 40 divides 3, it leaves remainder 1. So x1 equals to your 2. Next is second one. So it will be 15x2 is congruent to 1 modulo 4. 15, 1, 15, 15 into 2, 30. 15 into 3, 45. 45 when divides with 4, it leaves remainder 1. So x2 is 3. And your third congruence will be 12x3 is congruent to 1 modulo 5. So 12 divided by 5 does not leave remainder 1. 12 into 2, 24 does not leave remainder 1 when divides with 5. 12 into 3, 36 when divides with 5 it leaves remainder 1. So this gives us x3 is equal to again 3. So writing x here, it will be 2, it will be 3, it will be 3. Now coming to n. So n is equal to a1 n1 x1 plus n2 n2 x2 a2 n2 x2 a3 n3 x3 modulo n. Then statement for last. So it will multiply 2 20 20 3 15 3 4 12 3 and we'll take the sum. So n is equal to 2 into 20 into 2, it will gives you 80 plus 3 into 15 into 3, 135 plus 4 into 12 into 12, it will be 144 and modulo n is equal to n we have got 60. So this is equal to, if we'll add it, this equals to 80 plus 135, 144. It will be 359. 359 modulo 60. So when we'll divide 359 with 60, 65 times 300, so 59 is the remainder. So n is equal to 59. So 59 is the solution. Not n is equal to, it is x is equal to all the line. It's a blunder. X equals to x equals to x equals to. So x is equal to 59. Thank you for watching. Please keep on watching. Gradually, we will be continuing some more questions from Math Olympiad. So, continue to watch. Thank you.